All right, I think we're ready to get started. Thank you, everyone. My name is Andrew Pham. I am the Publications Chair here at the American Chemical Society's Cannabis Chemistry Subdivision. This month, we have a wonderful guest. Jini Curry is someone that I'm elated to have as a fellow analytical chemist. She's got very many great insights and discussions into the cannabis analytical scene. Jini Curry, if you don't know, she is the Chief Scientific Officer at Modern Canna Labs in Lakeland, Florida. She has a bachelor's degree with honors in biochemistry from the University of West Florida, and she has her master's degree in medical cannabis science and therapeutics from the University of Maryland, Baltimore. She's one of less than 400 people with this degree. Before entering the cannabis industry, she was doing research at several major institutions such as Emory University, the National Institute of Aging, and the University of Florida. She started working with Modern Canna in 2016, moved up to lab director in 2018, and got promoted to CSO in August of 2022. She's also involved in the Scientific Advisory Board for Analytical Chemists. She is a CAS Proficiency Testing Advisory Task Force with ALAC International member, and she's also on the CanMed 2023 Advisory Board. So Jini, today we'll be talking about the matrix effect and why cannabis testing is complicated. So Jini, go ahead.
Thanks, Andrew. All right, as Andrew said, I'm going to be talking a little bit about why cannabis testing is complicated and how the cannabis matrix affects that. So first off, if you are in a cannabis laboratory, you're probably familiar with this conversation of which result is going to be correct. There's differences among laboratories. So in this instance, a sample was sent for an pesticide analysis, and they were looking at bifenthrin in this product. And so it went out to 6 different labs, and all 6 labs got different results. And so we have 605 ppb, 300 ppb, 1100 ppb, pretty close to 600 ppb, non-detect, less than the LOQ, and 450 ppb. So as the provider, grower, whoever sent this sample out, they're left wondering, I wonder which one of these results are correct and whose data I can trust. And in this instance, the true value for bifenthrin was 600. So that lab that got 605 and 590 are the 2 labs that got the correct result. So why do results vary? One of the biggest reasons we see variations in results is going to be the fact that there's no standard methodologies. So there are some coming out slowly from AOAC, ASTM. There's some Agilent app notes. There's some Shimatsu app notes, PerkinElmer app notes, lots of different options for labs, but they don't all align with each other. And so this kind of creates a problem in the industry because labs are left wondering, which method do I use? Which method is the best? Which method is going to get me that most correct result? Another reason why we see results vary is ultimately preparation errors. So as an analyst, as a technician, if you do something wrong in your process, that is going to lead to the wrong result in the end. And so labs need to have different things in place to be able to ensure that these preparation errors are not happening. And then the final one is going to be matrix effect. And that's the one we're going to focus on today. Matrix effect is extremely important in cannabis, and in the rest of this presentation, you'll see exactly why. So what is the matrix effect? The matrix effect is going to be what happens when an analyte has an interference that causes the sample to have a different response. So basically, you normally would see a response of 500, you're seeing a response of 400 or 200 or 100 or no response at all. You're seeing that the matrix is impacting that analyte's ability to be seen. So this is, you can see ion suppression, you can see ion enhancement, you can see where, your response is going up, your response is going down. And what ultimately happens when this occurs is that analytes are being incorrectly identified and quantified. And so a lab may think, oh, this has this much of this analyte in it, when the reality is that it doesn't. And ultimately, until you do several spike tests and kind of see what things are impacting, what different matrices are impacting your analyses and how they're impacting your analyses, you're not really going to truly understand the effect that it has. So on the screen here, I have ethoprope, and this biggest peak here is going to be the recovery of ethoprope in solvent. And then you're going to see it in cannabis flower, you're going to see it in derivative product, and you're going to see it in hemp flower. So when you take this sample, if this is a sample for you, or in this instance, it's a CCV in order for us to show the variation in responses, but you run a solvent cal, and then you quantify your cannabis flower on it, your derivative product on it, and your hemp flower on it, you're going to be drastically under quantifying that. So if a sample, a derivative product, for example, has ethoprope in it, you're now under quantifying that ethoprope by almost 50%. And so in this industry, that can be very dangerous, because that's the difference in selling a product that is contaminated and not selling a product that is contaminated. And so laboratories really need to be aware of this, and they need to know how to combat these sorts of issues. So some of the analyses that are impacted by matrix are going to be pesticides and mycotoxins. And you can see matrix impacting pesticides on both the LC and the GCMS triple quads. However, what we're going to focus on today is really pesticides and the LCMS triple quad. So our experimental design. What we wanted to do here is to prove without a shadow of a doubt that matrix does have an impact on results, and that when laboratories are running samples for pesticides, they need to be using blended matrix calibrations. And so we have flower, derivative product, and edibles we're looking at here. And for our flower, we were looking at a high THC sample, a sample with average THC, a sample with low THC, and then a hemp sample as well. And so this is actually some PT material we received from NSI as part of our PT program for running our PTs. They send blank matrix that you run. And so we used this blank matrix as well. And then for our derivative products, we're looking at distillate. We're looking at some THC distillate, some CBD distillate, some CBN distillate. We're looking at some THCA isolate, some wax, capsules, lotions, balms. And then in edibles, we were looking at gummy, hard candy, and chocolates. So our extraction procedure for our flower and our edibles, we take 1 gram of sample and we added 25 mils of acetonitrile, and then we vortexed that, shook it up really well, and then eluted it through an Agilent Sample Q C18 column. And once it had been eluted, we brought that volume back up to that final volume of 25 to have that 25x initial dilution. And then we did a 10x dilution from that. And we did a 10x dilution of just the sample. And then we did a 10x dilution plus a pesticide spike to create our spiked sample. And then both of these samples are going to be run. And we did the same thing with our chemical or derivative product. And you can see it's 0.1 grams of sample, 5 mils of acetonitrile, sonicate, vortex, get it all dissolved, then make another 10x dilution for the sample, and then a 10x dilution plus that pesticide spike. So analytical process wise, what we did here is once we had all of that material extracted, that flour, those edibles, and those derivative products, we then ran those on a solvent calibration. So we ran both the sample and the spike, and that allowed us to really calculate what our recovery is. So when you spike those samples with those pesticides, how did they recover? You know that the sample is clean, you know how much you spiked with, so you can calculate exactly what your range was there. And then we also took those same samples and ran them on a flower calibration for the flower, an edible calibration for the edible, and a derivative calibration for the derivative products. And this is where we're getting ready to dive into the data. And I think you're going to find the data very, very interesting as we look at it and kind of see all of the different things we were seeing. So here is a solvent calibration, and this is the recoveries for flower products. And so we have 4 different flower types here. And you can see that we're looking at a percent recovery range of 80 to 120 is what I have outlined. So that's pretty standard in the industry for matrix spikes. For pesticides, you may get like a 70 to 130 kind of situation. But ideally, if you can keep stuff between that 80 and 120, it's going to be really good. And so you see that a lot of these samples, I mean, they're having bad recoveries for various analytes. They're having some over quantification of analytes. And then you do have this yellow sample right here. And this yellow sample is that hemp sample. So that's going to be something we talk about as well, because that one recovered pretty well, even in this solvent calibration. Then we went to our matrix calibration recoveries for the flower products, and you can see just how much tighter these recoveries are, as well as how many less analytes are failing low. So you can see that pretty much all analytes with the exception of, I would say, about 1, 2, 3, 4, 5, 6, maybe. I'll have those exact numbers for you on the following slides, but you can see that the recovery is much better and it's much tighter. So like I said, we're going to look at these each individually. So this is our high potency THCA flower solvent versus matrix. So the solvent calibration is going to be what is in red, and the matrix calibration, the sample being processed on that matrix calibration, is going to be what's in blue. And so you can see that for failures, so we're calling failures anything outside of that 80 to 120 range. So total failures low, so less than 80, and solvent was 12 versus matrix was 2. And then the total failures high in solvent was 6, and in matrix was 8. So a total of 18 failures in solvent and 10 failures in matrix. One of the things that I want everybody to kind of keep an eye on as we go through these slides is how the failures rates change from low to high. Because if you are attending as a regulator, I know you are probably like, I would love for them to over quantify rather than under quantify, because that's going to be a way to keep patients safer. Because if they're over quantifying and saying it has more of something, at least they're not missing that analyte, or at least they're not under quantifying that analyte. So we'll keep an eye on that as we go through these. And I think you guys will start to notice a trend of what we see when we do those matrix calibrations. So here's that average potency THCA flower. Again, the solvent calibration in red and the matrix calibration in blue. And in this one for solvent, we had 12 failures that were low, and in matrix only had 4 failures that were low. And then for high, we were seeing 11 in solvent and 10 in matrix. So failure-wise, we were going from total failures of 23 to a total failure of 14. And here's that low THCA flower. So this is a flower that I believe had about 5 to 7% THCA. So we wanted to see kind of, does that potency impact it, or does it do a pretty good job of correcting all of them? And so here we had 11 failures low in solvent, while we only had 4 low in matrix. And then we had 6 high in solvent and 10 high in matrix. So that total there is the difference between the 17 failures in solvent and those 14 failures in matrix. Here's that hemp PT flower sample. So this is one that I wanted to talk about a little bit, because this is something that cannabis labs tend to battle with. If you're a cannabis lab, if you're running PTs, you probably know this struggle where you see that the matrices that are coming in for the PTs don't really match the matrices of what you're seeing on a daily basis. And so this can create some issues for the laboratory where they're misidentifying or incorrectly quantifying something because of these interferences not being the same. So in this instance, you could run this on a solvent cal and you would recover fine. You would recover a little low for one of the analytes, but overall, there's not really much matrix impacting this, which also kind of raises the question about whether or not this material that we received was actually true hemp. And so I would be interested to kind of continue looking at that a little closer and seeing if we see that all hemp material doesn't have much interference, or if we're seeing that this is something specific to that PT. And so in this one, we saw total low failures in solvent were 1, and in matrix were 1, and then total high failures in solvent were 2, and in matrix was 0. So the total failures there were 3 and then 1. So this sample is going to be the edible samples. And for this, you can see that we're looking at 3 different types of edibles, again, measuring that recovery of 80 to 120%. And this is our solvent calibration. So edibles recover fairly well in solvent. You do have a little bit of a spread. You have some things recovering close to that 80, but really the matrix isn't too impactful. However, oh, wait, wrong slide. Sorry, you guys, my computer is dying. So this is the solvent cal. And so you can see here that they are recovering low. They're coming in, anywhere from about 60 to 110%. And once you switch that to that solvent cal, they all come up. You still have some recovering 80, but a good majority of them are recovering right there around 100%. This is our chocolate sample, I believe. I'm not sure how to make this go away. So this is our chocolate sample. And in this chocolate sample, we're kind of looking at that same thing. Our solvent is going to be in red and our matrix is going to be in blue. So those total failures low in solvent were 10 versus the matrix we were seeing 1 failure low, and then the total failures high were 1 and 1 in both. So this really reduced those failures in the sample from 11 to 2. Similar, this is the gummy sample. So in this, we were seeing 10 total failures low in solvent. We're only seeing 2 now once we calibrate in matrix. We were seeing 1 failure high and still 1 failure high. It's an analyte that recovers weird. So that's another thing we're going to talk about a little bit later about some of those pesky analytes and how to ensure you're quantifying those correctly. So again, taking those failures from 11 to 3 is a pretty large reduction in the number of failures out whenever you're spiking. And then here is a mint sample. Again, solvent and matrix calibrations, and you can see those total number of low failures were 11 for the solvent and 2 for the matrix. And then the total high failures were 1 and 1. So again, we really were able to reduce the number of failures from 12 to 3. And so that's great because that means that if you're reducing those failures, you're calibrating in matrix, there's less of a chance that things are being quantified incorrectly. The matrix is no longer impacting those results. So here's our derivative product. So we ran a total of 7 samples, but we actually only have 5 of them on here. I'm going to show you one of them at the very end, and you'll see why it's not on here. And then one of them, we were seeing some crazy internal standard suppression that was causing like double the recovery. And so again, something as an analytical chemist, if you're evaluating data, should be able to look at that and say, oh, this is a problem. This really can't be factored in because this sample has something weird going on. And that's something that if you're evaluating data in your lab and you see something like that, where your internal standard is being squished in half, you definitely need to rerun that sample and figure out how to correct it, even if that means creating a specific matrix cal to that matrix. But you can see you've got failures high, you've got failures low, you've got things all over the board. Once you calibrate in matrix, though, you really fix a good portion of these. You do have a couple analytes right here that are being a little finicky, but aside from that, most of these things are now recovering within range. And so we're going to look through those as well. So you can see here, we've got that solvent versus matrix. And in this one, it is going to be, I'm not 100% sure what product this is. So this is going to be a 1-to-1 THC to CBD distillate sample. And so this is going to be something that was about 40% THC and 40% CBD. And in this, you're seeing that we're taking those failures from a total of 19 failures to 4 failures. So originally, before matrix calibration, we were having 16 failures low. And that was reduced to 3 failures low once we did matrix, and then 3 failures high down to 1 failure high. So really, matrix does impact these results drastically. This is a wax sample. So again, we're seeing in this one, not as many failures across the board, but there's definitely still some failures, and there's a substantial number of low failures. And so we were looking at 6 low failures in solvent versus 2 in matrix, and then a total of 5 high failures in solvent versus only 3 in matrix. And then that total is being reduced by about 50% from that 11 to 5. This one is going to be a THC distillate. So this product was about probably 80 to 85% delta 9 THC. And so you're seeing here that 8 and 2 failures. So if you're running pure distillate, may not be as impactful, but you do still have to take this into consideration because some of these pesticides that don't recover well or recover high or recover low are pesticides that you commonly see in cannabis. And so you really want to be careful about that and make sure that you're taking that into consideration. And in this, we were able to take those failures from 8 to 2 in this process. Then we have an isolate sample. So this was a pure THCA isolate. And so you can see, again, we're really able to reduce those failures. And you can also see that these failures are a lot lower because the product is more pure. So the purer the product, we're seeing the less failures. So as you have less and less other things that are interfering and causing those interferences, you're able to eliminate some of those problems. And so in this one, we went from that total failures of 5 to 4. Not a drastic difference, but a pretty good difference when you're looking at low to high, I guess, because you'd rather have those high failures than those low failures. And then this is a water-based lotion. As you can see, the solvent and matrix calibration are very similar. This is because once you do that dilution, you have such a low concentration of that lotion in your sample that it's really not going to be impacting it that much. But still, it's also showing that you can still apply this solvent calibration to your lotion and it will work fine. And so you see we had those failures, 1 failure in matrix or in solvent versus 2 failures in matrix, but both of those failures were just barely a little bit high. So here, the numbers don't lie. So if you're looking at our failure tracking over time, so in flour, the average percent of failures overall was 26.3%, versus matrix was only 16.8%. And even more drastic is those average low failures, the change in those. So 15.5% in solvent to 4.7% in matrix. And so in the flour samples, we're seeing an overall reduction of failures, 36.1% overall reduction. And then for those low failures, we're seeing a 69.4% reduction. Similar, you have the derivative products. So the derivative products, we're seeing an overall reduction of failures happening by about 61%. And so for solvent, we had a 15.7% was our average failure. And in matrix, we were seeing 6.1%. And then again, reducing those failures low by 75% here. So going from 10% average low failures in solvent to 2.5% in matrix. And then finally, the edible samples. And then for these, what we're seeing is an overall reduction of failures for about 76.5%. So taking those from an average of 19.9% failures to 4.7% failures, and then an overall reduction of low failures of 83%. So really able to resolve those low failures and taking them from that 18.1% to that 2.9%. And that's really what we tend to see in edibles, is that they have a lot of those sugars and those fats in them. And so they're going to lead to those low recoveries without that calibration, matrix calibration, even though they weren't terribly out of realm. You had about 20% failures, 18.1% of those failures were low. And so that's the kind of things you have to take into consideration when you're deciding whether or not you need a matrix calibration for this. Here is our fun sample. So the sample I told you, it did not include, this is a CBN crude sample that we received. And this sample only had about 28% CBN in it. It was very distillate-like, it was very thick. We don't really have any idea what else was in that. And you can see that whatever else is in that is clearly impacting the recovery of these spikes. And so this is something that you need to be on the lookout for as well. So if you have a strange sample coming through the lab, you see something that's different, you're seeing weird internal standard responses, you need to figure out why, and you need to do that troubleshooting. And so in this sample, we can see clearly something is going on. Luckily, we didn't have to run the sample for pesticides. We actually just used it for this study. But I wanted to be able to show people just how much matrix can impact it, especially when you're not quite sure what matrix is in something. So with that, interferences happen. It's just the reality of things. You saw the sample on the previous slide. Cannabis is complex, and sometimes these interferences, they're just going to be unavoidable. There's nothing you can do to get rid of them. And so there's a couple different options of what labs can do if this happens. And one of those is going to be that they can do a larger dilution, right? So our final dilution is 250 for our flour and our edibles and 500 for our derivative products. And, you could do a much larger dilution. You could do a 10x on top of that and get a 2500x and a 5000x. But, yes, but the problem with doing that is it's going to then raise your detection limits. And in cannabis, you're looking at such low detection limits, and you need to see things so low that the larger and larger dilution you do, you now make it impossible to see your analytes of interest. And if you can't see your analytes of interest, you're never going to see them. You're never going to have hits because you've diluted all of those hits out. So the way that our lab combats this and deals with these interferences when we see them and indications that our QC is clearly showing us matrix is causing some sort of a problem, we do standard addition on our samples. And so standard addition basically uses the sample that is containing the problematic analyte and a certified reference material, so your CRM, your standard, and you build a calibration with that, and you're able to determine that true concentration of the analyte in question. If you're an analytical chemist, you will know this, but ideally you should include a 5-point calibration curve for this that's fortified both below and above the estimated concentration of the analyte. You could potentially do it with less points, but realistically, it's not going to provide as accurate of data. And if you want your data to be legally defendable, you're definitely going to want that 5-point calibration. And so to kind of see what we do here, for example, we have this sample, we have analyte A, and we can see that something's not right with analyte A. And so we want to do standard addition on it. So we take that sample containing analyte A and we spike it with analyte A at 1/4 the concentration, and then at half the expected concentration, at the same estimated concentration, at 2 times that concentration, and then either at 5 or 10 times that concentration, depending on what that actual compound is and how it responds. And what that allows you to do is then do an extrapolation of that calibration curve, and you can find that true concentration of that analyte. And so to show you guys really quickly an example of that to kind of help you better understand, we have a batch here, and you can see our CCVs were recovering well. We're recovering a little bit high, 125%, and the bottom one, 121%. Again, I would prefer things to recover high than recover low. And then you can see that the blank spike and blank spike dupe, so that is going to be a fortified blank matrix. It's going to be the same matrix as our calibration that we've spiked with 10 ppb of bifenthrin, and we can see those are recovering well. We're getting 118% and 107% for that. However, then you get to this MSMSD, and so these samples should have been spiked with 10 as well, but we're getting 17.5 and 16.3, and the source sample to this didn't have anything in it. And so for us, that really indicates there's something going on with matrix that could be interfering with the results. And so that's why when you see this sample here that has a hit, the sample has that hit of 0.22, we need to confirm that matrix is not leading to this result being increased. And so that's where we create this standard addition calibration. And if you are using Agilent, you have an Agilent LCMS triple quad, there's a portion within Mass Hunter that allows you to do standard addition, and the software will help you do these calculations. And so you can see you put in your expected concentrations, it builds a calibration, has your calculated concentrations. We run an ICV that's going to be a second source to confirm that calibration was good. And then we requant that. We basically extrapolate and requant that sample on that. And you can see that that raw value went from 0.22 to 0.09. And so with this, you're saying, oh, well, the lab over quantified. That's not as bad as the lab under quantifying. But this is just one example. And we see several instances in the lab where the opposite is happening. We're seeing several instances where our matrix spike will recover at 50% and a sample will be, the limit is 100 and it's at 75. And so you can't use that data because you can't confidently say that that sample is not over the regulatory limit. And most times if that is happening, once you do that standard addition, you do see that analyte come above the concentration of the regulatory limit. And so that's one of the things that labs really need to be considering when they're doing this is how can they ensure they're getting the most accurate results possible. So conclusions, by performing matrix calibrations, the laboratory is able to drastically reduce those failures in all 3 matrices. Additionally, most of those failures that did exist in matrix calibration were analytes that were failing high, above 120%. If you talk to any regulator, they're going to say, I would prefer something failing high than failing low. The matrix calibrations do not work on all samples, and that is something that laboratories need to be on the lookout for. They need to be on the lookout for strange matrices. They need to be looking out for weird things on their chromatogram and weird responses and all of that so that they can figure out what to do if that happens and if that matrix calibration isn't working for the specific matrix. And then ultimately, when that data indicates that interferences may be present, the laboratory needs to use something like standard addition in order to confirm those results. Because if that sample has the analyte of interest and it's not recovering properly, it's most likely not being quantified properly. And that is it for me. If anyone has any questions, I'm happy to answer them.
Thank you, Jenny. Hi, everyone. So this is the time for Q&A. We'll set aside about 10 minutes for this. If you have any questions, feel free to type in the chat. There should also be a Q&A box that you can click here in the Zoom. But Ginny, as a fellow analytical chemist, I was looking over that data and I noticed you had some issues with pyrethrins. We're seeing the same at our lab. Do you think that's more because of the amount of isomers that pyrethrins have, or is it something native to our matrix?
It's definitely, I think, the isomers. You have so many different isomers you're looking at. I don't know how many you guys are looking at. We look at 6 different isomers in our lab. So when we're looking at all 6 of those isomers, you do have some that aren't as good of responders. And so really trying to figure out also how to get those better qualifiers potentially to kind of help you see that those analytes better is one way to solve it. And then the matrix, the cannabis matrix, it's also super complex, so it could have a factor in that as well.
Super cool. Are you guys also using a GC triple quad as well as an LC? It seems like most of the data I saw was the MSMSD.
So in this one, we're just using, in this study, we just looked at the LCMS triple quad analytes. There's 5 analytes that we run on our GCMS triple quad as well. So we run it, when you add up the isomers, Florida's list is 77 with isomers factored in. So you're looking at 72 of those on LC and 5 of them on GC.
Awesome. Yeah, that seems to be the kind of standard going forward. Of course, there aren't really standard methods, but that seems to be what people are leaning towards for more accurate results. How many pesticides are you required to analyze in Florida?
It's a total of 77 with isomers.
Yikes. I think that's even more than California.
It's a lot. That's for sure.
Yeah, so I'm waiting on some questions, but doesn't look like there are many popping up in the chat. Oh, here's one from Matthew. He's saying it looks like flunocomid and coumaphos and chlorpyrifos are flaring low a lot. Is there something about their chemistry? I think you got this, Jini.
I'm not 100% sure on those, that question. I can definitely talk with one of our more skilled LCMS triple quad analysts and kind of touch base with them and see if they know anything off the top of their head that results in those weird recoveries for those analytes. I know there's several pesticides that the slightest little pH change, they're up and out and gone and they're never coming back. So it could be something like that. It also could be the acidity of them and the way that they're shaped. If you're not doing that 25-75 in your dilution, we do see issues sometimes with certain pesticides.
Nice. And I can't really speak to the other two, but I definitely know we've had issues with chlorpyrifos being a chlorinated compound that doesn't ionize well on LC. That could have something to do with it. I also wanted to ask you, Jenny, you of course talked a lot about matrix matching in your calc curves. What do you think are suitable substitutions for cannabis and cannabis products when you can't get a large amount of actual pesticide-free cannabis flower?
That's a difficult one. I would say if you can find clean hemp flower, that would be awesome. But again, hemp doesn't nearly, from what we've seen, doesn't have the same interferences that cannabis have. So it could cause issues. I know that there are potentially some like PT provider matrices that you could try and see if they have blank matrix they can send you. But what we try to do is when we find samples that are pesticide free, we try to keep them aside so that we can keep adding them into our list of things we can mix when we need calibration.
Thanks, Jenny. Michael is asking, what's the ratio of analytes to internal standard? Or at least, in other words, in the 77 targets, how many do you have an internal standard tied to? I guess you could answer that as your lab does it.
Yes, I think we are using a total of 6 internal standards, but I'm not 100% sure on that off the top of my head.
Yeah, and I'm presuming that of those 6, one internal standard can be tied to multiple of the analytes, right?
Oh, yes, definitely. Yeah, you're able to tie several of them. The state of Florida is actually looking to implement a new rule that whenever you do your internal standard, you're gonna have to have wherever your internal standard elutes, whatever analytes are quantified on that need to be within 2.5 minutes of it. So we haven't, this is in their draft rules. We haven't really figured all of that out, but that is one of the things the state of Florida is looking to define to make sure people are using internal standards and using the right internal standards.
Yeah, I suppose that makes sense, although I'm not really sure how much that's going to help from a state standpoint. It seems like the masses would actually be a lot more important than the retention times, but that's just me, I suppose.
Yeah, that's why a lot of this stuff is still it's all draft right now. So labs are going to be able to provide comments back, and we're really going to be able to kind of help them through what we're seeing on a daily basis in a lab versus what they're writing, not from that lab standpoint.
Yeah, just another reason we need scientists and local government people. Get to the polls. All right, I think that's about it for questions. If you guys have anything else, Ginny, is there a best place that we can reach you at? Maybe you can put your contact info in the chat if you prefer, or we can
Yes,
forward any requests to you.
I can definitely do that.
Awesome. Everyone, this is Ginny Curry on Matrix Effects in Cannabis. Thank you so much for joining us. Again, my name is Andrew Pham, your host, and we are being hosted by the Cannabis Chemistry Subdivision at the American Chemical Society. If you haven't reached out to join, please do. We're on the ACS website under the Division of Chemical Health and Safety. The recording of this webinar will be up on our YouTube page very shortly. So if you missed anything or you want to go back over the data, feel free to access it. Ginny, thank you so much for your time and thank you for a wonderful presentation.
Thank you for having me.
Goodbye, everyone.